Okay, so just to check if the stream is live. I'm gonna check over here, and yes, I think we are. Yeah, and yes, I think and yes, looking good. Let's see. Thinking good of this. Did anybody chat on here? So first off, um, okay, so hmm, no other pose estimation um got this good results. Um, what's more, I need to get so what exactly the data pose? Um, what are the things that they give to you? So, okay, latency is uh, okay. So higher, much higher, um, um, much higher average precision. Um, that comes with slightly higher bit of latency. Also, yeah, floating points and the parameters. Okay. So Data is the first real-time end-to-end transformer model for multi-person pose estimation, achieving outstanding results on the COCO and crowd pose datasets. In this work, we propose a new denoising technique suitable for pose estimation that allows object key point similarity metric to generate positive and negative queries. Additionally, we developed a new classification head and a new classification loss that are variations of the LQ head and the varifocal loss used in define. Um, so yeah, let's play this. This is about 200 FPS. Um, yeah, okay, so mm, yeah, I think this guy here is going to be more important for me in the long run. Um, yeah, just because of the key points it is detecting. I'm going to go with this guy and run the human checkpoints. Yeah, this is going to be much more useful for me because what I am looking at, what I'm hoping to get, this just does it well. I'm hoping to get the neck region and also, yeah, this is like way better. Yeah, yeah, cool. So that's the model I'm going to use. Let's go back to here. There's a Google Colab notebook. There's a Hugging Face space, which I'm using there. So these are the model checkpoints. This is about yeah, um, this is much better compared to these. So this is like a very fair model size. The medium works and works pretty well for yeah, and you can see that the delta from M to down to L and X is not as much as from M to N. So yeah, yeah, performance gains there. Looks good. Okay, I'm also going to test out just one more edge case where um, these things sort of fail. So this is front left. This is front right actually. Um, yeah, so it's occluded, so it thinks the hand is straight here, but it is not. But anyway, this is pretty impressive for parts that there's no way you could tell that the hand is not. Yeah, yeah. It's also the same as this, so makes a lot of sense. I'm going to choose the other one. Front. This was front. I think this is what I'm going to run now. Let's run this guy. Yeah, this one is like pretty good. Pretty good actually. So data pose and crowd pose, beautiful. Let's continue down here. We have, yeah, so they use it on a Tesla V100 GPU, right? Um, Byte size equals 1, FP16, Tensor RT 8.6.3. Yeah, so this is training usage. Trying to see if there's any inference code. Otherwise, I'm just going to go with the code from the Hugging Face space. Um, How do I need to export an environment variable there? Um, anyway, yeah, for a single file, Onyx, data pose, blah blah blah. Yeah, okay. For a folder, benchmark. Okay, cool. What? Oh, it's lambda.ai now, not lambdalabs.com. Cool. This is really nice. I will um yeah, okay. So this is all good. I think I'm going to go with what we have over what is this? Data tutorial. Uh, yeah, this is good. This is good. This is good. This is good. Clone the repo, blah blah blah. What if I just took the Hugging Face space? We have the files here, don't we? This is data repos with all the GitHub stuff, and then app.py. It's as easy as okay, I really is just doing the same thing as that. Okay, I might need to dig into the paper and find, because I'm trying to really go into details of what are the positions that we are getting, right? It's going to be very useful to me. So I need to find out what key points they are using. Um, yeah, I need to find out the key points. Uh, what are you using, man? Search for key points. This is like the one scenario where I think that um, I would use something like um, RAG if this. The RAG included in things like Copilot and all that. I have never uploaded a PDF and asked questions, but I'm going to do that right now. What key points, body landmarks does the work predict? Cool. Okay, so nose, neck, yeah, presumed location. That's crazy. That are opposed. Where are you getting this? Okay, so neck. Is it really nose? Because this here is like way above the nose. But then let's go back to the app. I'm sure if I dig into the code, I'm going to see something there that's going to pretty much let's reduce the confidence. That's too much. 0.4. This is just the one scenario where it's like really bad, really bad. Uh, the left and the right, right? Um, let's try the right at the left. Okay, let's try that. Mhm, mhm. So uh, I just think I'm going to avoid the lefts and the rights because they don't even look. It's so um, distorted. It no longer looks human, right? This does not look like a human, right? The proportions are just way out of shape. So yeah, let's get back to maybe this guy, the front. Okay, let's get back to the front, and yeah, I want to see whether uh, not exactly. I'm talking about crowd pools. Does it tell me this is for crowd pools? There are two. Or I just need to look at what crowd pools data is. Uh, because yeah, crowd pools data, and yeah, with 14 labeled key points and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, that's the mapping that I need to find out what it is. um, crowd pools. Anyway, this is fine. Um, yeah, I know it's crowd pools data. I know that this is. I need the crowd pools variant. Um, yeah, head center. Cool. Neck. Looks good. Left ankle, left knee, left hip, right hip. Okay, looks good. Um, key point. Anyways, yeah, we've got our answer. The AIs know what key points are. So, um, close. Let's get back to, yeah, we can close out of this. I no longer need to do this. A lot of this is just unnecessary now. And I can go ahead and delete that from our Google Drive. So I'm going to call this the pros estimation. Okay. I'll just go ahead and delete all of these guys. Delete, delete, delete. Okay. So, yeah, let's let's get to work on this. There's the tutorial right here. I'm just going to get out of this in this. Yeah, I still want to listen to that. Data pose. Yeah, they just glazed over. They did not. I don't think they mentioned the key point names, so they don't want to repeat the name of the key points. Everybody knows it's apparently I'm the only one that doesn't know what the difference is between a, a crowd pose key points set and the the no, so I don't want a GPU backend because this is just yeah, I'm the only one that doesn't know what the difference is between a crowd pose um uh, key point set is and a Cocoa key point set for poses. So rerun this, just importing the GitHub repo into our environment and copying the contents of the example there. Okay, so pip install pandas, upgrade, whatever. Let's do that as well. Okay, I'm going to keep this. Where is the tutorial? Okay, yeah, this is the tutorial. I was looking for this guy. Okay, so install this guy as well. Clear the outputs, and then what is this? Restarting kernel, import os.kyo, get PID, and then -9, right? np.rec. So what is np.rec? I'm learning a couple of things from this repo, from this tutorial. I want to see what np.rec is. So there is a way to restart your kernel without going into to like click on restart kernel. Okay. Okay. What is this? Sorry. Hmm. Module not found. Okay, I get what it is trying to do. So I think in the requirements, um, there's a specific NumPy, yeah, version that they use, and that version contains the rec module. And so if they don't, if this throws an error, that means we're in the wrong version of NumPy. So we're restarting the kernel, and we're sure that we have installed the right version of NumPy. It's just that the notebook, I can show that. Show NumPy. It's just that the notebook is not using the right version of NumPy. Yeah, this is good. Let's run this. It's going to restart the notebook, and programmatically just um, restart the notebook. Okay, so let's put this here. Run this. It's just appending the paths that we have for the repos and the inference tools um, there. So this here, let's copy it over and read what it does. So here, because we've been able to add this to system path, we can make this import. So we import the lazy config, we import instantiate, we import an annotator and an annotator crowd pose. I might not need these two things later down the line, but okay. So the config models for Cocoa, yeah, so we have um, basically these are files that I think define the networks, right? So data pools, configs, data pools. Are there really that much? Yeah, so um, it's quite a number of them. So let's look at the M, which is the thing that we are going to use. So here we have yeah, from include, import, blah blah blah, the model, criterion, training parameters, post processor, dataset train, dataset val, evaluator, lazy call, optimizer, EMA, and then the get params, get optimization parameters. So let's see, output directory, epochs, EMA. So how do I get rid of this? Um, okay, so it initializes the um, yeah first processor the number. Let's look at what we have in M. Yeah, yeah. By default, it is the Cocoa, and then we add the number of body points. Yeah, we add those things if we are working with the crowd pose variation, which has I think less than what we have in Cocoa, less key points than we have on Cocoa. So we have here transforms policy, epoch 541, just little variations here, base size, repeat, stop epoch, yeah, some other basic stuff. So this is a configuration that we add, and then the model name is M, and then we have the parameters and the config. All right, so I'm going to choose here crowd pools, okay, and then the download URL is data pools. So okay, in the releases, I put it in releases, model name, then put the drawer, initialize the drawer. Looks good. There's a lot of things that I'm going to um, um, pretty much um, just shed. I'm going to shed a lot of things. But in the meantime, let's keep on going. We know the things that we are going to basically shed. Okay, so we download the import that lazy config. If there's the attribute pre-trained, blah blah blah, and then the state equals load from the download URL. My application equals CPU, reads folder. Yeah. So the instantiate the model with the config that we get. Um, Post processor, instantiate the post processor that we get from the config, and then we just do some basic model loading, and then we have model equals model.deploy, processor deploy. Um, yeah, I think these are some things. Just making that and then put in the, yeah, just like and then we have like a simple model here that we're using, right? Instead of oh, I get this. Instead of having the model, I would say okay. So we have a transform for any image that we get, which is 640 by 640. Pretty important detail. Um, Pure import image, copy patches, show, whatever. So device is CUDA, otherwise we use the CPU, threshold is 0.5, and we have this result. So this is the tutorial. Okay, I'm going to have to do a lot of copies and pastes. Yeah, to do a lot of copies and pastes. So let's also copy this guy, the transforms person, transforms guy, and then also the actual inference notebook code snippet. And I think I want to see the size of this model. What do we get at the end of the day? Let's refresh this. We have weights, data pose. I don't know the size of this. Let's copy the path and the human reader full format, and then yeah, let's run this. 82 megabytes. Okay. Yeah, we get the pose. Really good. Okay, so what is going on here? So we set our device, set our threshold, set our model to the right device. Then we have the path to the image file, and then width and height, we get the size. And then original size equals torch.tensor. Um, Annotator equals drawer. Image data equals, okay, so there's an original size tensor. Cool. So image data equals transform. So we transform that pure image, and then we unsqueeze and then send it to the device. We put that to the model, and at the end of the day we get scores, labels, and key points, and we sort of feed that. Okay, so it outputs quite a bit of them, right? um, and then we have 4 key points scored in this. So I'm going to move this code to a separate cell and just see what's going on. What is in this course? What is in this course? Shape 1 by 60. Okay, so I think um, it's just unsqueezing them. Thought it had like multiple other, yeah, it's really just unsqueezing them. I thought it had multiple outputs. Okay, yeah, it might. uh, let's see something. If we lower the threshold, which we know is going to make a lot more predictions scale through, And if we look at the scores dot shape now, interesting. Oh, sorry, no, scores dot shape. Still 1 by 60. I'm going to go ahead and draw and see the results. So there's two detections here. 1, 2, 3, 4. There's two detections there, but this 60 doesn't exactly change. Labels doesn't change. Key points. Okay, this is what changes. Um, yeah, so let's see. If we put the threshold back to 0.5, what do we in fact get? Still get 16 by 2. Let's run that. Okay. Still get 60 by 14 by 2. Yeah, 2 keep. Okay, okay. Maybe it's dividing the patches, dividing the image into 60 patches. I have zero idea what this is, but I'm not really looking to understand what the code is doing or how that we get multiple poses out. I just want to know that it works on what I want. Let's get these guys up here, these guys up there, and we will run each left dot png just to make sure that we're getting. Okay, so what happens here? You say we get the first one, you say for score and key point in zip of key points and scores. If score is greater than the threshold, then our annotator dot key points, we send that. Do we send the image? Okay, we just put the annotator. Where does it link? Good, good, good. I was looking for where the annotator knows what the image is all about. So it takes the original, I think, image, right, before we transform it. Okay, looks good. Let's look how we get for left.png. Iteration over a0. Turns out that means that we did not output anything, yeah, meaningful. But if I do front, um, I'll delete this and run this guy, and yes, we still get the same output. Tight. Okay, so I need to find a way to, I need to understand like what this thing is doing before I move on to putting this in my cursor. Anyways, this is beautiful. It works, and it works very fast. Inferring on even a this is a CPU compute. I don't even have a GPU, and it's working like blazing fast. So all good here. I will go ahead and integrate this into what I, my workflow. This is perfect, really. It's what I was looking for. At first, I was thinking I had to, because most of the post estimation work that has been done really expects an image that, um, it expects images of people, right? It's not trained to recognize this as a person. This is just like a non-textured mesh thingy. But so usually what I found is that when I try to use the YOLO detectors that are available, so I think let me go to pictures. Yeah, when I try to use YOLO and the rest, I got I got this, which is like really terrible. if you think about it. It was just really terrible. But I think it's mainly because those were not trained to recognize things that are not textured human message, human, um, uh, that don't look human exactly. But then I believe that this is because we have a transformer architecture or something. That is why it is robust to this kind of input data. I will definitely read the code, read the um, the paper and find out what it is they did. But really, for now, it works. I'm really glad it works. This is saving me a ton of time because at first I was thinking, okay, this is my approach. A, I'm going to take a um, a YOLO, not really YOLO, but like any pose estimation um, data set which contains things like this, um, um, and then remove the background first and just basically crop out the human and replace it with something that's gray, something like this, maybe this color, just replace every single human in the image with this same color. And because the key points are still in the same positions, if I train or fine tune probably a YOLO model, a YOLO pose model, I was thinking I'm going to get a good sort of still get good performance. But then that effort was short-lived because very quickly it became hectic. So this is good. It's like really good. It has saved me. It promises to save me quite a bit of time and I don't have to take the other route.